talk about here in this chapter as well. So maybe I'll just talk about it up front here, and just to kind of tie it into what we're going to be talking about here. So nomenclature is all about naming, and we're going to talk about how we name everything. And there's really two types of compounds that we're going to talk about in terms of naming, and those are the same ones that you saw in chapter 12 if you watch those videos, and that is ionic compounds. And ionic compounds always contain a metal and a non-metal coming together. And as you talked about in the bonding chapter, what happens when the metal and the non-metal come together, because of really some of their periodic trends, which metals pretty much have all of these sort of properties that make them want to give away their electrons. So metals typically are situations where are elements that don't really want to hang on to their electrons. They're willing to give them up pretty easily. And it works really well when they come in contact with a nonmetal, because nonmetals pretty much have the opposite sort of properties. They have the properties of they do not want to get rid of their electrons, and they want to hold on to their electrons. And in addition, nonmetals not only want to hold on to their electrons, but they very much want to bring electrons towards themselves and gain electrons. So what happens when these two guys get together is a metal will always transfer an electron or so over to the nonmetal. The result of that is it makes ions, like we talked about, I think, in chapter 4, and ions are things that have charges. And metals, because they always will get rid of their electrons, will always become positively charged and what are known as cations as a result of losing electrons. And the nonmetals which gain electrons now will have more electrons than protons, which means they have more negative than positive charge, and they will end up becoming more negatively charged, and our nonmetals will become anions. And those are negatively charged by gaining electrons. And the important thing here, when we have an ionic compound between a metal and a nonmetal, is there's absolutely no sharing of electrons in this situation. So the electrons have been completely transferred from the metal to the nonmetal. The result of this is that opposite attraction is what holds that together. And that's what is sometimes referred to as the electrostatic attraction. And that is the positive and negative charge between the two ions. So what holds that together is this positive charge attracted to the negative charge. Again, no sharing of electrons. Something like, again, NaCl, sodium chloride is an example of that. The sodium there is a positively charged ion. The chloride is a negatively charged ion. And the other type of sort of compound we're going to talk about in terms of naming are what are sometimes referred to as covalent compounds, are sometimes referred to as molecular compounds. And the difference here is this is when we get two nonmetals together. And when we get two nonmetals together, because if you look on the periodic table, they're pretty much all hanging out in the exact same place, the upper right of the periodic table. They have very similar properties, and they all have the same properties in a sense. They all want to hang on to their electrons, and they want to gain electrons. So what happens when two nonmetals get together is neither one of them is going to give up its electron because they both want to hold on to it. So the best that they could agree to is we'll just share electrons. And that is when we get sharing of electrons occurring when two nonmetals come together. They will share electrons. And as you hopefully have seen in those lectures, the sharing of electrons could be equal sharing or unequal sharing, but there is some aspect of sharing of those electrons which holds that together, like in water, for example, H2O. Those are all nonmetals, sharing of electrons happening in this particular case. The hydrogen shares some electrons with the oxygen. The oxygen shares with some of the hydrogen. and they make this sort of compound. Now, one of the things that we're going to talk about, obviously, is how to name each of these type of compounds, either an ionic compound or a covalent or molecular compound. Now, one of the aspects of ionic compounds are they do have charges, and things with charges in solution are what are known as electrolytes. And just talk a little bit about electrolytes for a second here before we get into the naming part. Electrolytes are substances that produce ions in solution and can conduct electricity because of it. So, for example, there are strong electrolytes. And a strong electrolyte will 100% break apart into ions in solution. And because of that, they are very good conductors of electricity. They can conduct electricity really well. So, for example, a very common example that people use for electrolytes is like a light bulb. And if you put a light bulb that has some electrodes on it into a strong electrolyte, the light bulb will turn on and it will be very, very bright. So it will shine very, very bright. It can conduct electricity really, really well. So if you had a solution, for example, of sodium chloride, which is an ionic compound, it will 100% break apart into sodium ions and chloride ions. So in that solution, you have 100% of these ions floating around. So if you had a beaker of sodium chloride in it, you would have just sodium ions floating around and chloride ions floating around. You would have none of these guys still there in that actual solution. It is actually just 100% ions there. And because of that, it creates a lot of ions really quickly and conducts electricity really, really well because of the presence of those ions. There's also weak electrolytes. Weak electrolytes mainly stay together. But produces a few ions. And because it's able to still produce a few ions, it's still able to conduct electricity. But nowhere near as good as like a strong electrolyte, but it's still able to conduct electricity. So if you go to like the light bulb example, if you took a weak electrolyte with some electrodes and you stuck it into a solution that's a weak electrolyte, what will happen is the light bulb will turn on, but it'll be very, very dim, almost like it's dying. There's not like a great deal of electricity being conducted, but it's still able to do so. A lot of weak acids and weak bases are weak electrolytes. So something like hydrofluoric acid, which is actually a weak acid, when it breaks apart in solution, it mainly stays together, but it's able to produce a little bit of H plus and a little bit of F minus. And it mainly is this guy still together, but will produce a little of these free ions. So if you look at the beaker of HF, you would actually mainly see the HF solution still together, but you will produce a little bit of these free ions in there. And because it's able to produce a little bit of these free ions, it's able to still conduct electricity, but again, nowhere near as good as a strong electrolyte definitely could. The other difference that you actually will see sometimes in the actual chemical reaction or equation between a strong electrolyte and a weak electrolyte is actually the arrows. So in a strong electrolyte, it's a one-way arrow. Everybody's dropping off to the right there. Nobody's coming back the other way. They're just going to completely break apart. In a weak electrolyte, you actually have arrows heading in both directions, and that implies that there is a forward direction and a reverse direction that's occurring. So a forward and reverse direction. It's a like two-way street. The reactants can make products. At some point, those products will come back together and actually go in the opposite direction and make back the reactants. So you can think of it kind of like a two-way street. The strong electrolyte is a one-way street. Nobody's coming back the other way. Everybody's just dumping out. Here with a weak electrolyte, it could go in both directions. It mainly does stay together, but does break apart a little bit. The last type of electrolyte is a non-electrolyte, and a non-electrolyte will dissolve in water, for example, but you do not get ions. So even though it dissolves, you actually don't produce ions. So a common example that you're familiar with is sugar. If you took some sugar that was a solid, you could dissolve it in water, and you would get the sugar that's dissolved in the water. Sugar, though, is made up of carbon, hydrogen, and oxygen. Those are all nonmetals, which means they share electrons. So there's going to be no ions being formed in this case. The whole thing is just going to dissolve as one unit, and you will not produce any ions. And again, because you did not produce any ions, it will not conduct electricity in this case. So a non-electrolyte will not conduct electricity because there's basically no ions present. Any questions on any of that there? So most electrolytes and most strong electrolytes are ionic compounds, which we're going to talk about how to name them here in just a second. Again, a lot of weak electrolytes are weak acids and weak bases. And again, some non-electrolytes, things like sugar and stuff like that, are mainly things that are sharing electrons and dissolving as whole units. So let's get into sort of naming first. And before we do, let's just remind ourselves, which I think we saw in chapter 4, but just to make sure, when we do look at the periodic table, and we got group 1, we got group 2, we got group like, we'll go 3, 4, 5, 6, 7, and 8 coming down this way. Remember that when things are by themselves, again, uncombined with anything else, they really don't have charges from the periodic table. But what we're going to be talking about here, and also what was talked about in chapter 12 when we talk about ionic bonding, for example, we do get things that do have charges. So when these things actually get charges is actually in an ionic compound when they hook up with nonmetals, and you get that transfer of electrons that occur. That's really where we see charges occur. Now, there are certain things on the periodic table that have what are known as fixed charges, that no matter what the situation is, it will always make that particular charge. Everybody in group 1 will make a +1 charge. Everybody in group 2 will make a +2 charge. Group 3, and usually we're talking about aluminum here, is going to be a +3 charge. And those are all metals, right? We got our like staircase kind of coming down in this region. And metals will make positive charges because they're going to lose electrons, and +1, +2, +3. So when we look at something like sodium, which is group number 1, no matter what the situation is, no matter who sodium is attached to, if it has a charge, it's always going to be +1. You'll never find a sodium with like a +2 charge, +3 charge, +4 charge. It will only have that +1 charge. Same thing when you look at magnesium. Magnesium is right next to sodium on the periodic table, number 12. And it will have a +2 charge no matter what the situation is. You'll never find a magnesium with anything other than a +2 charge. Now, when we get to the upper right of the periodic table and the upper right of the staircase, where the nonmetals are located, They also have some fixed charges. Things in group 5 make a -3 charge. And again, we're talking about the nonmetals like nitrogen and phosphorus that are above the staircase is who we're talking about here. Group 6 is going to be -2. Again, we're talking about the nonmetals like oxygen, sulfur, selenium. Group 7 will be -1, which is our nonmetals like fluorine, chlorine, bromine, and iodine. These are fixed charges that they will always make. And that leaves us really this part of the periodic table where we have our transition metals. And also remember that below the staircase here, these are actually metals. So remember, above the staircase, they're nonmetals. Below the staircase, they're metals. On the staircase, they're semi-metals, which have properties above. Yes, sir. No, it wouldn't be actually a +3. We're going to actually talk about that in 1 second. But you're right, it will be positive because there really are metals in that region. But what transition metals have in common with these kind of metals that are below the staircase is they make a variable charge. So they don't have fixed charges. So they have a variable positive charge. And so do these guys over here. Things like lead, things like tin. These are not the right locations, obviously, for them. But in those areas, lead, tin, bismuth, all those kind of guys. I'm actually going backwards the way I'm writing it, but you get the idea. In that general region where you can find those guys, they can have a variable type of charge. So when those guys actually hook up with other nonmetals, for example, it does matter who they hooked up with and how many as to what the charge is for them. Yes, sir. You have a question? Yeah. That is talking about sodium and oxygen. Sodium would make a reaction with one oxygen, and you would actually need two sodiums to come together. Yeah. Yep. Yep. That is correct. Yes. Yep. So transition metals and guys just to the right and below do have variable charges. There is 3 exceptions in the transition metal region that even though they're transition metals, they actually have fixed charges. And the 3 exceptions are zinc and cadmium. They're right on top of each other there. They will always have a fixed charge of +2. And if you hang a left at cadmium, you will find silver, and silver has a fixed charge of +1. So this kind of backwards L right about here on the periodic table, even though they are transition metals, they actually do have fixed positive charges. So that is really important, understanding the charges as we get into the naming part here, especially with ionic compounds, because it's all about the charges and stuff like that. First off, any questions on that there? Now, another very important thing that I think we touched upon at the end of chapter 4 last time, but it's been a little bit. So just to remind everybody, when we put together anything that is positive and anything that is negative to make an ionic compound, the goal is when you put together your cation, which is positive, and your anion, which is negative, these guys need to be put together in the simplest way possible to get an overall charge of 0. It has to be neutral. So when you make a proper ionic compound and you put that positive and negative guy together, they need to balance each other out in terms of their charges. They need to equal 0 overall in terms of their charge when you do that. So for example, as was the question a second ago, when you take something like sodium, which is group 1, and it has a +1 charge, and you want to put it together with something like oxygen, which is group number 6 over there, that has a -2 charge. The idea is when we put these guys together, we need to get the overall charge to equal 0 when we write the formula for the ionic compound. And to do that, basically +1 and -2, I need not one sodium ion, but I actually need 2 of them. And those 2 sodium ions will give me a grand total of +2 that will balance out the -2 that comes from the 1 oxygen. And that is why when we write the proper formula for this, it is Na2O. Remember that the subscript goes to the guy to the left, right? So the 2 there means that we have 2 sodiums and 1 oxygen. Now, ionic compounds, when you write the formula for it like I just did there, will never have a charge. But they are made up of, obviously, things that do have charges. So there are 2 types of formulas that you sometimes write when you're dealing with things that are ionic. You may be asked to write the formula for an ion. So if you were asked to write the formula for a cation, you would need to write Na+. It needs to have the charge because it's an ion. If you were asked to write the formula for the anion, which is negatively charged, in this case, it would be O2-. You would need the actual -2 there written to indicate that it is an ion. Now, if you were asked to write the formula for the ionic compound, when you put those guys together, that is when we go to our Na2O, no charge. We balance out the positives and the negatives, and we get our proper formula. So whenever you take anything that's positive, anything that's negative, it should always equal 0 when you put it together. But it is still made up of things that do have charges, which are these ions. Any questions on that there? Okay, so let's get into really some of this naming here, I think. So first off, and we're going to see some more examples a little bit later on, there are certain things that when we go to name them, we do kind of use just like a common name. So messed up by a lot of people most of the time, H2O. It is not a trick question. It is water, and you should call it water when you're asked what is H2O. I love the answers I get sometimes when I put H2O on the test, but it's not really a trick question. It is water. So most people, it is steam and ice, but most people should refer to it usually as water. And it is not, as we'll talk about maybe a little bit later, is not dihydrogen monoxide, because nobody wants a refreshing glass of dihydrogen monoxide, right? They would much rather have a refreshing glass of water. Probably wouldn't sell as great, I suppose, if you called it that. So you should always use water when you see that. NH3 is ammonia, and NH3 should not be confused with an ion we will see later on, which is NH4+. So there is something that looks very similar to it. But this has no charge, it's neutral, it's ammonia. It's actually a weak base, believe it or not. It's a weak base and a weak electrolyte. CH4 is the simplest organic molecule you could have. That is methane. That is the stuff that comes out of your Bunsen burner gas thing where you light it, right? So that is the gas that you set on fire, is methane. So any of these 3, you should roll with these names if you do see them. So the first thing we're going to talk about is naming binary compounds. And binary compounds just basically means we have 2 things coming together, 2 different elements, and we want to name them. They are, again, broken up like I talked about at the beginning here. They're broken up as either an ionic compound, which is a metal and a nonmetal, or it is a covalent compound or molecular compound between 2 nonmetals. So once again, no sharing of electrons here, sharing of electrons there. So again, if you watch over chapter 12, I'll go take you through that idea. So we're going to start with ionic compounds, and when we name an ionic compound, as I just mentioned a second ago, there are a couple of rules you should always follow. The first rule is, as we just talked about, if you're going to write the formula for it, it does need to equal 0, the compound formula. Also, it should always be positive guy first, followed by negative. So it should always be the cation first, then the anion. And that order should go both in the naming of a compound and also when you write the formula. So when you write the formula or you write the name for it, it should always be the positive guy first, followed by the negative guy. Now, if you have just the ions by themselves, not in an ionic compound, but you have a formula for an ion like we saw a second ago, like for example, H plus or Na plus or Mg2 plus. And as we talked about, I think a little bit there at the end of chapter 4 as well, anything that's a positive ion, the way that we name these guys is essentially, in most cases, we just use the name of the metal, except for hydrogen, which is a nonmetal. We just use the name of hydrogen. And we just put ion at the end. So this would be the hydrogen ion. We just use the whole name of the element. This would be the sodium ion. This would be the magnesium ion. So if you have a positively charged ion by itself, not combined with anything else, it should have a charge like all three of these do. And you just simply use the name of it, and you could put ion at the end of it to indicate that it is an ion. Now, if you have something that is negatively charged, like maybe you got H minus, maybe you got Cl minus, maybe you got O2 minus. By the way, hydrogen is the only element that could go both ways. It can be positive and it also can be negative. In most cases, hydrogen will be positive. Hydrogen will be negative if it comes after a metal. So for example, if you had something like LiH, in this case, this is lithium, which is a positive metal, and in this case, the hydrogen actually is a negatively charged guy in this case. And we still here, as you can see, have +1 and -1, which is why when we write the formula, we basically just need one of each of them. When we put it together, that gives us 0, right? +1 and -1 in this case. Negatively charged guys, which are anions, as we talked about, I think, in chapter 4 as well, we basically use the front part of the name and we drop the last part of the name, and sometimes a little bit more than the last part, and we replace it with IDE. So IDE is what ends up at the end. So instead of the H minus being hydrogen, we drop some of that hydrogen part of the name, and this is what is known as the hydride, IDE ion. Instead of Cl being chlorine, because it has a charge, we drop the last part of chlorine and we put IDE at the end of it, and this is known as the chloride, IDE ion. And same thing here, this is oxygen. Instead of using oxygen, we drop a little bit of the last part of the name, put the IDE there, and this becomes oxide. We drop a little bit more than the last part there, and this is known as the oxide ion. So negative things, and probably 8.5 times out of 10, if it is a negatively charged ion, it probably comes from the periodic table if it ends in IDE. Yeah, so anybody there in the non-metal region will end in IDE at the end of it if it has an ion or an ionic charge to it. Any questions on that there? And again, as we saw earlier, that is why when we took our sodium, which is +1, put it together with our chloride, which is -1, again, +1, -1 means we just need one of each of them. And that is how, by the way, we get to the name of sodium chloride in this case, right? IDE at the end of it. So we basically kind of put both names together to get the name of that particular ionic compound. Any questions on that there? So again, if you're asked to write the formula for an ion, it should have charges. But if you're asked to write the formula for an ionic compound, which is a metal and non-metal together, it should have no charge, and the charges should be balanced out to 0. Now, when we talk about ionic compounds, there are two types of ionic compounds. So type 1 and type 2 refer to an ionic compound. And again, an ionic compound, always a metal and a nonmetal together. Again, as we talked about earlier, no sharing of electrons. Electrons have been transferred in this case, and it's that positively charged and negatively charged that basically hold that together. A type 1 compound, and in general, when you are naming and you see a metal, that is the most important thing. Yeah. So if you see a metal in any type of formula, or really even in a name, that is really the most important thing that you should look at. It is really the thing that will determine how you should name that particular compound. So a type 1 compound is where the metal has a fixed positive charge. So type 1 is a fixed positive charge for the metal. And as we talked about there a second ago, that is basically group 1 on the periodic table, group 2, group 3, which is aluminum, silver, cadmium, and zinc. So if you're looking at a formula of a compound that contains any one of those metals in it, what should go in your head is that is a type 1 situation, and I should name it as a type 1, which we'll talk about how to name it in just a second. But that is what you want to think about always when you're looking at a formula, for example, or even if you have a name, what you're trying to figure out is really two things. You want to figure out, first off, what type of compound are you dealing with? Are you dealing with an ionic compound? Or are you dealing with a covalent compound? If it is a metal and nonmetal, it's ionic. Like I said, it's kind of a no-brainer there. It's going to be ionic. And then if you know it's ionic, the next thing you want to ask yourself is this a type 1 ionic compound, or is it a type 2 ionic compound, which is what the metal will tell you. So what is a type 2 ionic compound? Again, the metal is the most important thing, and the metal there can have a variable positive charge. So as I drew a second ago, that's our transition metals, are just to the right underneath the staircase, where we have lead, tin, antimony, all those guys. These are guys that have a variable positive charge. And again, on the periodic table, that is essentially your transition metals. And just to the right, where things like lead, tin, etc. are located underneath the staircase. So, for example, chromium, which if you look at chromium number 24 in the periodic table, dead smack in the middle-ish of the transition metal region. In certain cases, chromium can make a +2 charge. Other cases, chromium, for example, can make a +3 charge, maybe a +4 charge. Copper, also 29 there on the periodic table in the middle of the transition metal region. In certain cases, copper can make a +1 charge. In other cases, it can make a +2 charge. So when we're naming things, metals are involved. That is always where you should look at, and that will guide you as to how to name them. And like I said before, the first thing you want to do is figure out what type of compound, ionic or covalent. And then if it's ionic, the next thing you want to figure out type 1 or type 2 for ionic. And again, that's going to point you in the right direction in terms of how to name it. Any questions on that so far? So here's a table from your book of just individual ion names. And as you can see here, anything that is positively charged, pretty much just the whole metal name is used. Anything with a negative charge will get that IDE treatment at the end of it. Again, dropping some or a lot of the last part of the element name. All right, so let's talk about type 1 here and how we get to it. So if you have a type 1 compound and you want to actually name it, again, the process you want to go through is, all right, it's ionic. And I know it's ionic because there's a metal and non-metal present. And it's a type 1 because of the metal, which again is always the thing you want to look at. It has a fixed positive charge. So the good news is if you had something like that, let's just say we had, again, our NaBr. We'll do this, right? So when I look at NaBr, the first thing I want to look at is Na is sodium. That is a metal. Br is bromine, which is a nonmetal. So that sort of looking at it tells me it's ionic. And once I've determined it's ionic, the next thing I should look at is the metal. And when I look at the metal, which is sodium, I can see sodium is in group 1, which means it has a fixed positive charge. And that means that this is going to be a type 1 compound. And as soon as you do those two sort of questions and you get yourself to it's a type 1, frankly, that is all you need to name this thing. You don't have to figure out anything else other than those two things. It's ionic, that metal's type 1, it's a fixed positive charge. You pretty much are all set to name it. How do we name type 1 compounds? We start with the whole name of the metal, and the nonmetal gets the IDE treatment at the end of it, and that's it. So when I look at NaBr, I go ionic, check. Sodium group 1, fixed positive charge, check. Type 1, I'm ready to name. So whole name of Na is sodium. Br is bromine, but it's a negative guy here, so it becomes bromide, IDE, sodium bromide in this case. Here, when we look at the ionic compound, there is no charge, but this thing is made up of two ions. The cation here, which is our positively charged, is a sodium with a +1 charge, right? Because it's group number 1. The formula for our anion, which is our negatively charged ion, it's group number 7 on the periodic table, and that has a -1 charge. Once again, that is why we only need one of each of these when we put them together. +1 and -1 equals 0, and it's neutral, no overall charge in this particular case. Any questions on that there? What is the real reason we need to put these things together to equal 0? It is actually in the chapter 12 lectures about bonding. It actually has to do with bonding. What happens when sodium loses that electron? If you look at where sodium is located on the periodic table, it is number 11. When sodium loses an electron, it goes from 11 electrons to sodium with a +1 charge to 10 electrons. And 10 electrons on the periodic table is one behind sodium, and that is neon, number 10. And what happens is when sodium loses that 1 electron to chlorine, it backs up to the same electron configuration as neon. It is what is sometimes referred to as being isoelectronic. Isoelectronic means it has the same electron configuration as somebody else. That's really important because neon is what type of element? Neon is a noble gas. And noble gases are chemically inert. They're super stable. And that is the purpose of all bonding, is for everybody to become like those noble gases, which are really stable. They don't become those noble gases because sodium here still has 11 protons and is still sodium, but it becomes like neon because it has the same type of electron configuration as neon does. What happens to chlorine when it gains that electron? If you look at the periodic table, chlorine is number 17, which means when chlorine starts in this process, it has 17 electrons. When chlorine gains that 1 electron, it now has 18 electrons. And if you look at the periodic table, number 18 is right next door. and that is our friend argon, right? And argon is also a noble gas, right? And now by chlorine accepting that electron from sodium, it now moves forward on the periodic table and ends up with the same electron configuration as argon in this case, which is a noble gas. So by sodium losing this electron and by chlorine gaining the electron in this case, both of those elements can now achieve what is known as noble gas configuration. They have a very stable electron configuration, and what that creates now is a nice stable bond. And the reason why we have to put the positive guy together and the negative guy together in the simplest way to get to zero is that ensures that all those elements end up in a noble gas configuration. So it actually has to do with the bonding aspect of it and the losing and gaining of electrons that creates everybody to become super, super stable, for example. Yeah. Any questions on that there? Okay. Now, when we look at an ionic compound like sodium chloride, like I said before, even though the overall compound does not have a charge, the metal and non-metal, when you write it together, it is still made up of two things that do have charges, like our sodium ion and chloride ion. Same thing here. If we look at Ki, and we were going to go through our sort of ritual here to help us name it, the first thing we would look at is K is potassium. So again, that is a metal. I is iodine, which is a non-metal. So right there, that combination of metal and non-metal checks off the ionic box. Yeah, so I know this is an ionic compound. And once I know it's an ionic compound, like we were talking about, the next thing I want to identify is it a type 1 or type 2 compound? And that means I look at the metal always. I always want to look at the metal. So in this case, my metal is potassium. And if I go to the periodic table, potassium is group number 1 on the periodic table, which means potassium has a fixed positive charge of +1. And that is a type 1 compound. And now that I've identified the metal as a type 1, that's it. That's all I need to name this. I'm going to go with the whole name of the metal, which is potassium. The iodine, drop the last part. I'm going to add the IDE at the end of it. So this would be potassium iodide. By the way, the I here has a -1 charge because it's group number 7. So once again, -1 and +1 gives us an ionic compound that's equal to each other in one of each of those. Same thing's happening with each of those elements. If you look at the periodic table where potassium is sitting, potassium loses 1 electron, which means it backs up on the periodic table to argon, which is 18 electrons, to the noble gas that comes before it. If you look at iodine on the periodic table, it gains that electron and actually goes forward on the periodic table to xenon, which is a noble gas. And now, again, in this situation, by potassium giving away its electron, iodine gaining its electron, they both achieve noble gas configuration, and they make a nice stable bond in that case. And again, that is really the whole purpose of all bonding, both ionic and covalent bonding, is for that to occur, things to get to the same electron configuration as noble gases. Question on that there. By the way, that is also why, as we did earlier, when we look at sodium and we look at oxygen, for example, when they look at the valence electrons, which was talked about there in chapter 12 as well, sodium has actually 1 valence electron, which is the highest energy level electron, represented, for example, by that dot. And those valence electrons, because they're highest in energy, they're actually furthest away from the nucleus, which means they're not held as tightly, and those are the electrons that are involved in bonding. Oxygen is actually group number 6 on the periodic table, which means it has 6 valence electrons. I'll just do it like that, 6. Now, what happens when sodium loses an electron, it could come over here to oxygen, right? Now, when oxygen gains that electron, it will gain that 1 electron. the sodium will lose the electron. By the way, that is when sodium becomes +1, when it loses that electron. Now, what happens to oxygen in this situation is, how many electrons did oxygen just gain? 1, which means it has one more electron at this point than it did when it started. And it actually will make a -1 charge, right? But it's not going to be happy if you just look at where oxygen is located on the periodic table. Oxygen is number 8, right? And if it only gained 1 electron, it now has kind of 9 electrons, right? That puts it at what element? Puts it at fluorine, right? Fluorine is not a noble gas, right? It's not going to be super stable. By the way, as you know, hopefully from watching chapter 12, it did not just meet the octet rule either, right? It doesn't have 8 electrons. So it's not going to be really happy in this case. So what happens in this situation is we actually made sodium happy, right? Because it backed up to, for example, neon. But the oxygen is like 1 electron short. So what happens is we need not just 1 sodium in this case. We actually need 1 more sodium that has another electron that it could kindly donate over to that same oxygen. When it does, that sodium now becomes +1 charge. This sodium now gains that second electron that is needed to give it a -2 charge. And now oxygen gained 2 electrons, which will allow it, if you just want to look at the periodic table, move 2 spaces. And now it's at neon's configuration. So by gaining those 2 electrons, 1 from each sodium, that allows the oxygen to achieve that noble gas stable configuration. And it actually allows each of those sodiums to also gain neon's configuration. All 3 of those elements now, by gaining and losing electrons, have now achieved that noble gas configuration. It makes it really stable for them to be attracted to each other. And now we have +1, and +1 is a +2 to balance out that -2 charge. And that is why when we put something like those guys together, that is why we end up with this formula here, because we need both of those sodiums to give away an electron for oxygen to be able to achieve that noble gas configuration. Yes, sir. Basically ending up with the exact same electron configuration as a noble gas. So for example, sodium, when it starts, has 11 electrons. Yeah. And when sodium loses an electron, it actually ends up with 10 electrons. And that's the exact same number of electrons that regular old run-of-the-mill neon, which is a nice stable noble gas, is. So it then ends up being the same electron configuration as that noble gas neon. And the same thing with oxygen here. Oxygen, when it starts, has only 8 electrons, but it needs to gain 2 electrons, in this case, of this example, 1 from each sodium, to get itself to 10 electrons total. And now that oxygen, by gaining those 2 electrons, have now also achieved neon's configuration. Yes, sir. Yeah, you could do, like, for example, a lot of those man-made elements, for example, on the bottom there. That's, in a sense, how it can be done. There's a lot of, you could shoot particles, you could shoot like neutrons, you could shoot alpha particles, you could shoot different particles at elements, and it will change things, like, for example, in the nucleus, which will actually physically change an element into something else and make a new element. In terms of electrons, you would have to sort of coerce the electrons off of the way by having something there that's going to try to remove it and stuff like that in a situation. But again, a reminder that although these things, for example, in this last one here, those 2 sodium ions and the 1 oxygen ion, all achieve noble gas configuration, they are still both sodiums and oxygen. They do not change elements, because the only way they can change elements is you would have to change the protons, and we're not talking about doing anything with protons. It's just all electrons here. So they still remain the same element. They're just in a much better position in terms of their electrons. They're in a much more stable condition in terms of their electrons, but they still remain the same element. So they don't really change elements. Other questions? All right. So why don't you try some here and see what you come up with? So for each of these, give the proper names, and let me give you some formulas so you can write our names so you can write the formulas here. So why don't you write, let's do magnesium. I'll do nitride. Let's do aluminum oxide. And let's do, kind of want to go through the questions to direct you in the right spot. So again, if I was looking at the first one here, I see K, which I know is a metal. I see Cl, which I know is a non-metal. So right away, that tells me I'm checking the ionic box because I got a metal and non-metal. That then directs me to always, when a metal is involved, take a look at the metal. And I see K, and I look on the periodic table. I see K number 19 there, group number 1, and that tells me this is a type 1 metal. And that's really all I need at this point to name it. So now that I know it's a type 1, just going to go the whole name of the K, which is potassium. And the Cl here is going to become chloride IDE at the end of it. Now, again, the cation here is K plus, is the formula of the cation. The anion here is group 7, which is Cl minus. And again, that is why the formula is just one of each of them, because plus 1 and minus 1 equal each other. Any questions on that one there? Coming to the next one, zinc is a metal. S is a non-metal. So again, that's going to check the type or the ionic box. Since a metal's involved, I'm going to look at zinc. I see zinc is a transition metal, but it is one of those 3 that we talked about that actually has a fixed positive charge. So because of that, it is going to be a type 1 metal. And again, at that point, that is all I need to name this. I'm going to use the whole name of my metal, which is zinc. Sulfur is going to get the IDE treatment at the end of it, and this would be zinc sulfide. The formulas for the cation and anion here, zinc is always plus 2, so that would be our cation formula. And our anion here is group 6 for sulfur, which would be a minus 2 charge, would be our anion. Yes, sir. Do you have a question? No. So type 1 is always metals that are from group 1, group 2, or group 3 are zinc, cadmium, and silver. The metal is always the most important thing, and that what they all have in common is they always have a fixed charge. No matter the situation is, they will only make, for example here, zinc will only make a plus 2 charge no matter what the situation is. The IDE is always for the non-metal that has a negative charge. So it is always the non-metal guy. That's just an element from the periodic table. We'll have IDE at the end of it. Type 1 versus type 2, like what information tell us? It's going to tell us how to name it. So we haven't talked about type 2. We're going to talk about it next, but there is some additional things you have to do for a type 2 that you don't do for a type 1. Yeah. Yep, no problem. Other questions? Okay, taking a look here. I got calcium, which is a metal. I got bromine, which is a non-metal. So again, that's going to check the ionic box. Always metal involved. That is my focus of what I want to look at. I see calcium as group number 2, which means it has a fixed positive 2 charge. So that checks the type 1 box here. At that point, I'm ready to name. We're going to go whole name of my metal, which is calcium. And the non-metal gets the IDE name. So bromide here, IDE instead of bromine. Now, what's not there that maybe some of you put there? There is no prefix, yeah? People want to go dibromide because there's 2 of them. Don't do it unless you want an X, yeah? You do not use prefixes ever, 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 ever. One more time, just for good measure, ever if there is a metal involved. Yeah. So if you got a metal hanging out there, you got a type 1 or type 2 ionic compound, you should not be using a prefix. Yeah. There's very few situations where you might see a prefix with a metal, but it should never really be there. So the good way to remember it is if you have a metal, probably should not have a prefix for sure. There is a special place for where we use prefixes we'll talk about. It is definitely not in any ionic compound type naming of type 1 or type 2. The reason we do have a 2 there, though, is for the reason of balancing out the charge, right? So calcium is a +2 charge because it's group 2. Bromine, our bromide, is group 7 is -1. So by the way, if you were asked to write the anion for the Br part, that is what it looks like. This guy, the Br minus. This is our cation. Again, the reason we have 2 of them, the 2 there is -1, -1, -2 to balance out the +2 charge that is there. That is what that 2 means, that we have 2 of those. By the way, there is nothing like this other than an X. Yeah. So when you're asked to write the formula for the anion, it's just the Br minus. Again, the 2 should not be on the bottom either. Yeah, or anything like that. Question. So no prefixes for sure in this situation. Coming down here, we have barium, which is a metal. Remember, hydrogen is actually a non-metal, even though it kind of acts like a metal sometimes. So in this particular case, that checks out ionic. Here we have barium, which is group number 2, fixed +2 charge, checks off our type 1 box. I'm going to go barium on this one. And this is actually the negative version of hydrogen. So that is barium hydride. In this case, we have a barium with a +2 charge. We have 2 H minuses. And again, that's what the 2 is for. And that gives us -2 on the hydrogen side to balance out the +2 on the barium side. Any questions on any of those there? All right, so if we have the name and want to write the formula, we still kind of take the same approach. So magnesium is a metal. Nitride is nitrogen, which is a non-metal. So this checks the ionic box. The best thing to do is just to keep it simple, which is you should just write the basic 2 ions that make this up. So magnesium, which is group number 2, means I have a magnesium with a +2 charge. Nitride, which is nitrogen, group number 5 on the periodic table, means it has a -3 charge. Again, remember, we're putting something that's positive and negative together. We need to equal 0 in the simplest way possible. If you're not sure, you can actually just multiply the numbers together. Common number there is 6, right? So at this point, what we want to think about is how do we get each of these guys to 6? So magnesium, you would need not 1, not 2, but you would need 3 of them, right, to get to 6. If you add all those guys together, that is +6. The nitrogen there, you just need 2 of them. If you add all those guys together, that is -6. By the way, if you do it like I just did there and it helps you, all you have to do at this point is just count what you wrote, right? So that is 1, 2, 3 of those, so a little bit of a 3. And that is 1 and 2 of those, so a 2. And there it is. Yeah, just kind of put it together like so. Now, I will say sometimes people are taught to move the charges down from the top, and that will give you the subscripts, and that works, 93% of the time. So if you're good by just blindly doing that 93% of the time, you will get a lot wrong. So sometimes it's better just to think about it as balancing it, and if it helps you to write it out or draw it out, so you can visually just count up what you got going on, that's a good way of doing it. But if you just want to blindly kind of move the things down and up, you will get some wrong as you go through them because they won't always work correctly. If we look at aluminum oxide here, aluminum is a metal. Oxygen is a non-metal, so that's ionic. So again, we're just going to find the 2 basic ions here. Aluminum is group 3, which means +3. Oxygen here is group 6, which is a -2. Once again here, to equal 0, 6 is our common number. To get my aluminum to 6, I need a grand total of 2 of them. And to get my oxygen to 6 there, I need not 2, but I need 3 of them. So that is 1, 2 aluminums, number to the right, and 1, 2, 3 oxygens, number to the right there. And there's my formula in this case. Yeah. Any questions on that one there? Lastly here, sodium sulfide, metal, non-metal, ionic, maybe. Sodium is group number 1, so a +1 charge. Sulfide is group number 6, which is a -2 charge. In this case, common number there is 2, right? You can multiply them together if you can't see it. We really actually need more of the sodium. We need 1 more there to balance it out. Again, if we count up what we got going on, 1 and 2 sodiums and 1 sulfur. And there it is. Yeah, just like so. Best not to overcomplicate things. Yes. I will when we talk about the next one. How's that? If you wait about when we get to the next type of naming, we'll definitely come across one where it will not work. Yeah, for sure. Other questions? All right. So that is type 1 naming. Why don't we take like a 10-minute break or so, and then we'll get into the rest of it there. Okay, we're going to get started here again. So we've now talked about type 1 ionic compounds. And again, remember, you want to kind of go through the process, figure out is it ionic or really covalent? And is it type 1 or type 2? Obviously, we talked about type 1 here. We're now going to talk about type 2 and sort of the different sort of thing that you need to do with type 2 versus type 1 ionic compounds. So let's take a look at that here. So type 2 ionic compounds are also still ionic. So they're still ionic compounds. They are still a metal and a non-metal together. So once again, you're still going to basically identify it that way. Always, as I've been mentioning, if you have a metal involved and you're doing naming, that is the most important thing. So the type 2, as we talked about earlier, metal is one that has a variable charge. So it can have a variable positive charge. That again is pretty much our transition metals, obviously except for those 3 that we did for type 1. In addition to our transition metals, just to the right, again, underneath the staircase where we got like lead and tin and so forth, those guys, although they're not technically transition metals, they also have a variable charge. So what is the difference between type 1 and type 2? There is not a giant difference in terms of how you name it. You still use the whole name of the metal, just like you do in type 1. You still give the non-metal the IDE treatment, just like you do in type 1. The main difference here is you do have to insert in between those two a Roman numeral. Now, the Roman numeral is oftentimes mistakenly thought of what it means. So what does the Roman numeral mean? The Roman numeral is the charge, which is the positive charge, on one of the metals. So if you took out just one of the metal ions in a type 2 compound, the Roman numeral indicates the actual positive charge it is. It does not indicate how many metals you have, which is a common mistake people make. People think, like, they see up 2, it means you have 2 of those metals. So again, the Roman numeral indicates what the positive charge is. So for example, if we look at this guy here that's in the example, the FeCl2. Now, I'm going to still take the same approach that we've been talking about, which is I see iron, that's a metal. I see chlorine, that is a nonmetal. So once again, that is going to check off the ionic box, just like we did previously. As we've been talking about, if you check off the ionic box, you then need to look at the metal. It's the most important thing. When I look at the metal in this case, and I look at the periodic table, I can find iron dead center, actually, at number 26 there, of the transition metal region. As soon as you see that iron is a transition metal, that should check off for you. It is a type 2 compound. And then it should check off for you, I need a Roman numeral. Yeah, so that is kind of what you want to think about. These are things you did not have to think about when we did type 1. You could just go right into the naming, right, once we identified it. But here we do need to kind of use the Roman numeral. That also means that you need to figure out what is the charge in the case of iron. Iron can have multiple types of charges depending on what it's attached to. The good news is in this situation is you will 100% of the time always know the charge of whatever it's attached to. So for example, in this one, although I may not know what the charge is of my iron, I do know that it has a Cl, right? And I do know that Cl is group number 7, which means it has a -1 charge. But how many Cl's are there in this formula? Not one, but 2, yeah? So it actually has not one of those, but 2 of them there. That gives, for my negative charge, an overall charge of -2, 1 for each of them. We do know that this is an ionic compound, which means when it comes together, it needs to equal 0. And in this case, that would mean the iron must have what type of charge to balance it out? A +2, yeah? So it's got to have a +2 charge to balance out. Now that I've determined that, now I got everything I need to name. So again, we're going to use the whole name of the metal, which is iron. We're going to use a Roman numeral 2, not for how many irons we have, but for the actual positive charge. So again, that is where the Roman numeral comes from, the positive charge. Once again, just like in type 1, and there's a metal involved, it does not matter how many of those chlorines you have, it is still just chloride. Again, no prefix here. So this is iron Roman numeral 2 chloride. Question on that name there. Now, why do we need this name? What happens if I had this guy, FeCl3? Again, if we go through the same process, that is our metal, that is our nonmetal, it's ionic. My iron, again, is still a transition metal, which means it's type 2. Here I have an iron with some type of charge. I have Cl, which is -1, but in this case, I don't have 2. I have 3 of them, which gives me a -3 charge. That means in this particular case, the iron has what type of charge? A +3 charge, yeah? And that means that this name would be iron Roman numeral 3, again for the positive charge. And once again, doesn't matter how many of those guys we have, it is just chloride. The purpose of the Roman numeral is to tell the person in the first case, we're talking about the iron with the +2 charge. And in the second case, we're talking about the iron with a +3 charge. Why do we not need to do that with type 1? Because those guys have fixed charges. Sodium can only have +1, so you don't need to tell people it's a +1 because that's the only charge it can ever have. So because these guys could have multiple positive charges, you need to include in your naming the Roman numeral to indicate what the positive charge is, so you can basically tell people which one you're dealing with in this case. Any questions on that there? All right. All right, so why don't you try this one here? Okay, so let's take a look. Once again here, if we look at it, we got Pb, which is a metal, that's lead. Oxygen is a nonmetal. So once again, that should check off the ionic box. We're going to always look at the metal whenever a metal is involved. when we look at lead, which is Pb, it is not really a transition metal, but it is one of those ones to the right of it and below the staircase that does have a variable charge. So because of that, that is going to check the type 2 box. In this case, we have one lead ion. Now, oxygen we know is group number 6, which means it has a -2 charge. And there's not just one of them there, but there is 2 of them. That's going to give us a -4 charge. And that means that the lead here is actually +4 in this case, not +2. An example you're asking for that it doesn't work right there. So that is one where if you just flopped it over, you go with lead 2, which is a common answer people would give in this one. And it would be incorrect in this case. So this is lead number 4 for the charge on it. And once again, it doesn't matter how many you have, no prefixes here because we have a metal involved. So it's just going to be oxide in this case. So again, this would be definitely one where if you did kind of the flipperooski there, it's not going to work so well as you go through it. You know, same idea. Another example, for example, if you had, say, something like this, what would be the charge on the Mn? It would be +6, yeah. So this is oxygen, which has -2, and there's 3 of them, which would be a -6. This guy would be +6 in this case, yeah. So there's a lot of examples. Like I said, I mean, it works more times than not, but probably around the 93 percentile. If you just randomly do it without thinking, you'll get the right answer. But there is a number of ones that you can't come across that kind of flipping around, it really won't work correctly. Yeah, for the most part, because those guys could have a variable charge, you know, you could get some things that have some weird positive charge that might not be what you think it is. Yeah. Other questions on that there? And by the way, if you were to name that would be, this one would be manganese 6. And again, it would be oxide in this case. And you'd use Roman numeral 6. Now, we do use these Roman numerals. And there is an older system that we're not going to personally use in this class, but you do sometimes come across it in papers and manuals and stuff like that. And an older way of naming without Roman numerals is to use kind of like the old school name of the elements. So, and end it with either ic or OUS. And ic means the larger positive charge, and OUS is the smaller positive charge. So for example, if you had iron 3, that would be ferric versus iron 2, which would be ferrous. And if you had like copper 1, that would be cuprous. And if you had copper 2, it would be cupric. So those are some older names that are sometimes still used. Mainly copper and iron, people still like to use those kind of names and stuff like that. But we are not going to use it in this class. We're going to exclusively use only Roman numerals for this type of names. But again, you may see it in a book and stuff. So especially with copper and iron, people like to still sort of use those names. But we're definitely going to not do that. And here you can see these sort of older names for some of the other ones here. And that's what I was saying, ferric and ferrous, cupric, cupric. But we're not going to use it here. We're just going to use the more systematic name. Now, one of the other sort of type 2s that is quite confusing for people is mercury. And mercury is kind of a weird one as well. So you could have mercury that looks like this. And you could have mercury, you know, that looks like this. Now, oddly as it is, the one that has all the 2s is actually mercury 1. And the one with only 1 2 is actually mercury 2. So this is actually mercury 1. And this is mercury 2. The reason that is mercury 1 actually comes as what's known as a dimer. It's basically 2 mercury 1s kind of hooked together. And that's where the 2 on the bottom comes from. They come as like a 2-pack, if you will. And that's why the 2 is on the bottom. How do you know it is the 2 versus the 1? That 2 that's on the bottom will typically still hang around. So for example, if you had this versus this, Which one is mercury 1 and which one is mercury 2? This one up here is mercury 1, right? That 2 is on the bottom. And this is actually mercury 2. There's no 2 on the bottom here. That one top one would be mercury 1 oxide. The guy on the bottom would be mercury 2, Roman number 2 oxide. The reason we have just one oxygen is this is -2 overall. This is +2. This is +2 and -2 in terms of the charges. So again, that's how we get to 0. So typically that little 2 on the bottom kind of hangs out there still. You could kind of still see it. And that's usually how you could kind of know it's the mercury 1 versus the mercury 2 sort of guy. Question on that there. All right, so as we've been talking about, the rules for naming type 2 are pretty straightforward. It's essentially the same thing as type 1. The additional step he has to take is figure out the positive charge on the metal and use the appropriate Roman numeral for it. That is again going to be your metal that's a transition metal or just to the right. The 3 exceptions again are the type 1 transition metals, zinc, cadmium, and silver. You do not use Roman numerals for those guys as you go through it. So why don't you try these here on the left? Let's go with names. And on the right, let's go with formula. Okay, let's take a look. Again, going through, we got CO, which is cobalt. That's a metal. Cl is a non-metal. So once again, checking off our ionic box. We want to focus always on the metal, which is cobalt. That can be found right there next to iron on the periodic table, number 27. That tells us transition metal, so that's going to be a type 2. That does mean we need to kind of figure out the charge if you're not sure. So we do have one cobalt. We do know that Cl is group 7, which should be -1 in group 7, and there's 3 of them. So again, if it helps you to just draw it out, draw it out. We got -1, -2, -3 overall. Tells us that our guy here should be a +3 to balance it out. Now we're ready to name it. Whole name of the metal, cobalt. We need a Roman numeral 3 for the charge. And once again, doesn't matter how many of those chlorides we have, it is still going to be just chloride at the end. Any questions on that one there? Yeah. You kind of do, yeah, for sure. So again, I would say to the left of the periodic table, to the right, and kind of the middle-ish. Again, we're not going to probably do too much with the very bottom-ish rows, those bottom 3 rows, if you will. The 2 on the bottom and the 1 right above it. But definitely kind of left, right. Middle right is a lot of where we kind of deal with for sure. Okay. Coming this way here, we got Cu, which is metal. I is non-metal. So again, going to check the ionic box. Looking at copper, number 29 up there is a transition metal. So that's going to check the type 2 box. Just rolling through our normal procedure here. Not sure what the copper charge is, but I for sure know I is group 7, which means it should have a -1 charge. Again, the goal here is to get to 0, so in the simplest way possible, and that in this case would just be a +1 for the copper. That is again going to give us whole name of the metal, copper, Roman numeral 1 for the charge, and IDE at the end there, iodide. Any questions on that one there? Coming next, we got SN, which is actually tin, which is a metal. BR is a non-metal. And again, that's going to be ionic. Tin is one of those guys, once again, that is technically not a transition metal, but is located to the right of it, below the staircase, in that like lead, tin, bismuth sort of area. So it's going to check that type 2 box. So once again, I may not know the charge of it, but for sure I know BR is group 7, and that means it has a -1, and there's not just one of them, but 4 of them. So if I just drew out all 4 of them there, That is going to give me a -4 charge, which means in this case, my tin should be a +4 to balance it out to 0. And that's going to give me a tin Roman numeral 4 here and bromide at the end. Any questions on any of those names there? All right, so we have the name and we want the formula. The good thing on this is the name in this case actually just tells us everything that we need. So when I see something that says iron 3, that means the iron has what type of charge? Has a +3 charge, right? So it works backwards, nothing to figure out there. Oxide is oxygen from the periodic table, which is group number 6, has a -2 charge. Once again here, common number between these guys is 6. To get the oxygen to 6, you need 3 of them. To get the iron to 6, you need a total of 2. You could count it up. That is 2 irons. And that is 1, 2, 3 oxygens. And there it is right there. Just basically count it up and write it together. Yeah. Any questions on that one there? Nickel Roman numeral 4 chloride tells me my nickel has a +4 charge because that is the Roman numeral. And chloride is group 7, which means it has a -1 charge. In this case, we need to get to 0, so we need not 1 Cl, not 2, not 3, but we actually need 4 of them, right, to balance it out. That means we have, I'll go to the top here, 1 nickel and 1, 2, 3, 4 Cls. And you can put it together there for NiCl4. Any questions on that one there? Lastly, we have tin 2 phosphide. So tin is Sn, and the 2 means I have a +2 charge. Phosphide is phosphorus on the periodic table, which is group number 5, which means it has a -3 charge. Again, if the common number there is 6, so we just need to get everybody to 6. So in the case of the P, we would just need 1 more. And in the case of the tin, we would need a total of 3. So 1, 2, 3, and 1 and 2. And there it is, yeah. Any questions on formulas or names here? Huh? All right. So that's type 1 and type 2. They are both ionic compounds in terms of their naming. The next thing we're going to talk about is here's just a summary there. Again, if you have some type 1, you do not need Roman numerals. And again, if it is a type 2 transition metal, you do need some Roman numerals with it. All right. So why don't you take a second and name each of these here and see what you come up with. Transition metal, one of those ones we talked about. So again, if you're not sure in this case, we can go to our oxygen, which is group number 6 and should have a -2 charge. That means that here our mercury is a +2. Is that mercury 1 or mercury 2 in this case? This one is mercury Roman numeral 2 in this case. And it would be oxide. Again, it does not have the 2 on the bottom. Yeah, so no 2 on the bottom there. And that would be mercury 1 if it did have the 2 on the bottom. Looking at the next one, we have Mg metal, non-metal, so ionic. Looking at magnesium, which is group number 2, so that tells us it's a type 1, so there's nothing to figure out. We could just proceed right to naming at this point. We're going to go whole name of our metal, which is magnesium. And we're going to go IDE there again for our non-metal, which would be bromide in this case. Taking a look at the next one, lithium metal, oxygen non-metal, so it's ionic. Looking at lithium, it is group number 1, which means it's a type 1 compound. So once again, nothing to figure out. We could just roll right into our naming. Lithium and oxide in this case. Once again, much like when we have numbers on the second guy, we have numbers on the first guy here, no prefix, still no prefix here, so don't use it in this situation. Coming here, Cr is chromium, metal, F is fluorine, which is a nonmetal. We find chromium there at 24 on the periodic table. Transition metal tells us it is a type 2, so we do need to do some additional work here, right, and get our charge. So again, we have one chromium. We know fluorine is group 7, which means it's -1, and there's 2 of them, which means that's a grand total of -2. So once again here, to balance that out, that's got to be +2. And that is what we need here. Chromium, Roman numeral 2, and fluoride in this case, again, for the charge. Any questions on any of those names? Yes? We have not. That's actually up next slide. Yep, we'll hit it right now. Yep. All right. So again, type 1, type 2, always metal, non-metal. That's always the situation. And like I said before, whenever the metal's involved, that is who you should look at to kind of direct you in terms of, really in this case, do you need a Roman numeral or not? It's basically what you want to look at the metal to help you decide. All right. Here's a little decision tree in case you need to decide kind of what we've been talking about there. So to answer your question you were just asked, and maybe the question of when should I use prefixes, this is the situation here. So this is the situation where you should use prefixes. Type 3 are actually covalently bonded. So this is covalent bonding happening here. And this is between 2 nonmetals. So this is the sharing of electrons. So with a type 3 compound, just like with type 1 or type 2, when you see a metal or nonmetal, you know it's ionic. When you see 2 nonmetals, you know it's covalent, and it's going to be a type 3 in terms of naming. So here's where we use prefixes, and the prefixes we use: mono for 1, di for 2, tri for 3, tetra for 4, penta for 5, hexa for 6, hepta for 7, octa for 8, nona for 9, a little deca maybe. I'm making this up. I don't know. 10. There we go. So these are the prefixes that we use, and I'll be completely honest with you. Type 3 compounds are probably the easiest of them all to name. But they're also the ones that most people screw up on because they think, well, it's got to be a little harder than that. So let me do some things I shouldn't do. And they start putting weird things in it with it. So type 3 are really the simplest things. Because it is covalently bonded, because they are sharing electrons, there are no charges. So you don't have to figure out charges. There's no ions. There's none of that. You frankly just need to pick the right prefix to use, and then you can name it. So the way that we name type 3 is, it is always the whole name of the first element, and you could use the prefix before that if needed. Then you use a prefix for the second name, and the nonmetal name there gets the normal IDE treatment. So prefix the first name if necessary, prefix the second name, and the second name gets the IDE. So for example, capital C, capital O. Those are 2 nonmetals together, carbon and oxygen. That tells me it's type 3. Now, there is also a really important rule, which is we do not use mono on the first name, but it's okay on the second. So you don't use mono on the first name, but you can use mono on the second name. The other thing that very commonly occurs when we're doing type 3 and we use these prefixes is we will sometimes get 2 vowels that back up to each other. So for example, we may get 2 O's that back up to each other in the name. one O from the prefix, one O from the element name. We may also get an A and an O that sort of back up to each other. Typically speaking, when we get these situations, we do not keep the prefix there on the vowel part of the, or the vowel on the prefix name. So, excuse me, we get rid of the vowel on the prefix there and we keep the other one. So this is a good example that will illustrate all these rules. So we have C, we have O, and that is carbon and oxygen, two nonmetals. That tells you type 3. At that point, you should be super happy. There's nothing to figure out. All we have to do is pick the right prefix. So one carbon is mono, but since that is the first letter and the first name, we don't use mono. So we just use carbon. So no mono on the first name. We have one oxygen here, which means we can use mono as our prefix, and we can use it on the second name. And this would be mono, and then the oxygen gets the IDE treatment, and this gives you monooxide, which doesn't sound great. That is two O's that back up to each other. So we don't call CO carbon monoxide. We call it carbon monoxide, right? And we get rid of the O on the prefix, and this is carbon monoxide would be the right name. So mono not on the first name, okay on the second. You get two O's that back up to each other, get rid of the first O. If you have an A and an O that backs up to each other, get rid of the A from the prefix. Oddly, two I's, they're okay. So if you have two I's, it's okay. But basically an O and an O or an A and an O, get rid of those prefixed vowels. Any questions on that there? Nothing to balance, nothing to figure out. Right prefix and adjustment on the names there. All right, so as I mentioned before, we use our prefixes. The way that we name it is the first element first, followed by the second one. Now, there is sort of an exception for hydrogen, and hydrogen really is a nonmetal, as we talked about. But for a lot of reasons, hydrogen does, in a lot of cases, in a solution, kind of behave more like an ion. And even though hydrogen is a nonmetal, we actually just name hydrogen like a type 1 metal. So what I mean by that is if you had HCl, which by the way is sharing of electrons between the hydrogen and the chlorine, it's covalently bonded. But in terms of naming, we actually don't name it really like, you know, kind of like a type 1, like a type 3. This would be known as hydrogen chloride. If you had H2S, for example, and these were gases perhaps, this would be hydrogen and sulfide. So it doesn't matter if there's multiple hydrogens or anything like that. We don't use a prefix with it. So hydrogen is kind of unique in that case. You could kind of think of it as really just more like a type 1 type of naming of it, even though technically speaking, in each of these cases, they're covalently bonded, they're sharing electrons and all that kind of stuff. The reason for that is something we'll talk about at the end of this chapter, which is when these guys get dissolved in water and they make an acid, they then behave more like ions in solution. And that's why we kind of name them like type 1. But all other nonmetals, we pretty much will roll with type 3 naming. Remember as well, though, we do have things like NH3, right, which is ammonia. And we don't use nitrogen trihydride or anything like that. We also have, you know, H2O, which is, again, water, not dihydrogen monoxide, right? So, again, don't use those sort of names. Use the common name. And also we saw methane, I think, before as well. Here's a table of those prefixes. And again, like I mentioned before, typically AO or OO will drop the kind of prefix vowel. Here's a couple of those examples, as we talked about there. Instead of tetraoxide, we will get rid of the A, and again, just kind of roll right into the oxide part without the A on the prefix. All right, so why don't you try, give the names of these guys, and why don't you also give the formulas for the following. Let's do dinitrogen pentoxide. Let's do carbon tetrachloride. Let's just make something up that doesn't probably exist. Disulfur hexabromide. Why not? Sounds fun. All right, so names on the left there, formulas on the right. Okay, let's take a look. And like I said before, these really should be the quickest ones that you do because there's really not much to figure out. You just got to kind of choose the right prefix and basically name it or write the formula. So here, the first thing I want to look at is what we're dealing with. So I see an I and I see an O, and those are both nonmetals. They're in the upper right of the periodic table there, or the right-hand side. And that tells me it is a type 3. And again, you should be really happy at that point. Nothing really to figure out. So we're just frankly just going to look at the prefixes there and the subscript. So 2 goes to the guy to the left. So that is 2 iodines. So the prefix for 2 is di. And we do use the whole name of the first element. So diiodine. Prefix for 7 is hepta. And that is oxygen. Remember, the second one gets the IDE at the end. And that's going to be hept oxide. Here again, we will drop the A off of that prefix so we don't get the A and the O that back up to each other. Any questions on that one there? Down here, carbon nonmetal, oxygen nonmetal, once again tells us type 3. So there's 1 carbon, prefix for 1 is mono, but we do not use it on the first name. So we will just use the whole name, no prefix. We have 2 oxygens, so we can use obviously di here, and oxygen is oxide, so carbon dioxide in this case. Lastly here we have phosphorus, nonmetal, chlorine, that's a nonmetal. We have 1 phosphorus, so no mono on that first name, so phosphorus. Here we have 3, which is tri, and chlorine becomes chloride. So phosphorus trichloride. Any questions on any of those there? Now, probably the ones that should take you the quickest is the ones here on the right. So basically, you just have to write what it says. As soon as I see prefixes, I know it's type 3, which means I don't have to figure out charges, I don't have to figure out balancing or any of those things. I simply need to write what it says. So di is 2 and nitrogen is N, so that's an N2. Oxide is oxygen and penta is 5, so there it is. Again, nothing to balance, just basically writing what it says. Carbon, no prefix, but I do see a prefix here, which means tetra, and also is a type 3. I do know that if I have a type 3 with no prefix on the first name, that is how many of those? 1, right? That's mono, basically. So carbon would just be C. And tetra is 4, and Cl is chlorine or chloride. So CCl4 would be our proper formula. Again, nothing to balance in this particular case. Lastly here, di prefix, hexa prefix. So di is 2, sulfur is S. Hexa is 6, and bromide is Br6 in this case. Any questions on type 3? Again, this is where you should use the prefix. You should probably never, ever, in most cases, you be using a Roman numeral and a prefix together. If you are, you should just put an X yourself over the thing and save me the trouble. Yeah, so if you find yourself Roman numeraling and prefixing, not a good thing. You're probably doing it incorrectly. Yeah, so Roman numerals are only really for type 2 metals. Prefixes are only for non-metals and non-metals together. Any questions on that there? Okay. So here's a review of what we just talked about. Again, type 1, no Roman numeral, no prefix. Type 2, only Roman numeral. Type 3, only prefix. Yeah. And again, both of these are ionic. This is really covalent or molecular here. All right, the next type of naming we're going to talk about are ones that contain polyatomic ions. And what are polyatomic ions? Polyatomic ions are actually groups of nonmetals that are together. They're actually sharing electrons, but they have an overall charge on them. So they're actually ions. So polyatomic ions are groups of nonmetals that have charges. If you look at NH4NO3, if you break it up right about there, you actually have two different polyatomic ions. This guy is NH4 plus, and this guy NO3 minus. This one nitrogen and four hydrogens are all sharing electrons and bonded together. They never break apart into individual things. They move around as a whole unit, and this whole unit has a +1 charge. If you go through the chapter 12 lecture, you could draw the Lewis structure for this. It looks like this. All those guys are sharing electrons, and it has an overall charge of +1. That one nitrogen and three oxygens over here are also all being shared in electrons, and it has an overall charge of -1. And if you drew the Lewis structure for that, which I think we probably did in that video there, it will look something like this. So ultimately, this is an ionic compound, which just like we talked about with type 1 and type 2, when we put an ionic compound together, the overall charge needs to equal 0, which is why when we take +1 and -1, we just need one of each of those polyatomic ions basically pushed together. Each polyatomic ion has a special name. This is what is known as the ammonium. Not, by the way, not ammonia, which is NH3, no charge. This is NH4 +1 is ammonium. Again, oftentimes confused with ammonia that has no charge and one less hydrogen. This guy, by the way, is known as the nitrate ion. The good news about polyatomic ion, if there is good news, is we simply just use the name of it. So regardless of how many polyatomic ions you have, you just simply use the name. So for example, if we were going to name this guy, we would basically just put both of those names together, and this would be known as ammonium nitrate, would be the name of this guy. First off, any questions on that there? By the way, for the most part, this is one of your few positive polyatomic ions. Most polyatomic ions are actually negatively charged. And there are a few that are positively charged, but most are negatively charged. So what does that mean most of the time of what happens? Most of the time of what happens is you will find yourself with a polyatomic ion that's negatively charged, and you will find it hooked up with a metal that's positively charged. So most of the time, you're going to have a metal and a polyatomic ion. And what that means is whenever a metal's involved, the one thing that we need to figure out is, do we need a Roman numeral or not? So a lot of times when you're doing polyatomic ion naming, you go back to type 1 or type 2 naming, where you look at the metal and decide, do you need a Roman numeral or not? And you put it together. So for example, if I had NaNO3, and I broke it up right there, this is sodium, and that is my nitrate. And here we would look at the metal, and that is a group 1 metal, which means it's a type 1 metal. And this would be sodium, and whole name of our polyatomic ion, nitrate. Now, if I took, for example, iron and threw it together here with my nitrate, iron is also a metal, and this is a polyatomic ion. What type of metal is iron, type 1 or type 2? It is type 2, which means you need a Roman numeral, right? So same situation. I know I have 1 iron. I have nitrate here, which is NO3 minus. I have how many nitrates? 3 of them. That means I have a -3 charge, and that means the iron in this case is +3. And the name of this guy would be iron Roman numeral 3, just like we did previously for the charge. And even though there are 3 nitrates, it has no effect on the name. It is just nitrate at the end. So that would be iron 3 nitrate. So I would say most of the time, because polyatomic ions are mostly negatively charged, they do find themselves hooking up a lot with metals which are positively charged. So in a lot of cases, you will default back to kind of like type 1 or type 2 naming and just use the polyatomic ion. First off, any questions on that there? By the way, what other thing did I do when I wrote the formula for that FeNO3? What is around the NO3? Parentheses. And whenever you write a formula that has more than 1 polyatomic ion, you need parentheses. That is because if I did not write the parentheses and I wrote it like this, what does that mean? I have how many oxygens? 33, which is not what you mean, right? Because you could clearly see here you have 3, 6, and 9 oxygens only. So you do need to always put brackets or parentheses around the polyatomic ion if there is more than 1. If there is just 1, you don't need the parentheses. But if there is more than 1 polyatomic ion, you do need to put parentheses around it and a subscript on the bottom to indicate how many you have. Any questions on that there? All right, so let's take a look. Here's a chart from your book. And you already know what I'm going to tell you, right? So since you took chemistry here at Saddleback, you do need to know these, yeah? So they're not going to be provided for you. So this table, I think I also posted one up on Canvas, which might be this table as well. There's a lot of similar ones on each of them. So you should be familiar with them. So you do need to know the formulas and the charges and also the names. Now, there is a good way to sort of remember these, and I'm going to kind of talk you through maybe a couple of ways that might make it a lot easier to maybe try to remember all these names and stuff like that. So first off, let's look at the patterns that we see when we look at these names. For example, if you look at something like what we have here, we have NO2 minus. That is nitrite. This is NO3 minus, which is nitrate. This is SO3 2 minus, which is sulfite. And that is SO4 2 minus, which is sulfate. Now, when you look at those things, for example, this NO2 minus and NO3 minus, This entire thing again stays together, has a -1 charge. This entire thing stays together, has a -1 charge. What is the only difference between really those two things? The number of oxygens, right? The guy on the left has 2. The one on the right has 3. They both have a -1 charge. This again is nitrite, ITE. This is nitrate. When you look at sulfate there, SO4 2 minus and SO3 2 minus. What is the only difference between those two? The number of oxygens, right? One has 4 and one has 3. They both have a -2 charge. This is sulfate. This is sulfite. Now, the first pattern that you see with these is in a group of 2 that are related to each other. The one with the most oxygen in a group of 2 will end in 8. The one with the most oxygen. You could think you ate too much. That is the one with the most oxygen, yes? Or not, I don't know. The one with the least number of oxygens ends in ite. So when you're comparing a group of 2 that are related to each other, the one that has the most oxygens will end with 8, and the one with the least will end with ite. What does that mean? That means if you want, you could just remember maybe all the 8s. And all you have to do if you need a ite is just take off an oxygen. Everything else stays the same. Charge stays the same. Everything else stays the same. Just take off one oxygen, right? Or if you want, you can remember all the ites. And if you need an 8, just put on one oxygen. Everything else is the same. So an easier way to remember is, if you don't want to remember everybody individually, just remember, okay, SO4 2 minus is sulfate. I need sulfite. I'm just going to take off one oxygen because that's the only difference. Everything else will be the same. Charge will be the same. Everything else will be the same. Now, there are some other things that you sometimes will see. There are groups of 4 that are related to each other. Right here is our common group of 4. And actually, here, I'll just do it here. Not do that, do this. So if you look at ClO4 minus, ClO3 minus, ClO2 minus, ClO minus, every single one of these guys all have a -1 charge. Every single one of these guys are all sharing electrons. So this is a group of 4 that are related to each other. If I break that group of 4 right about here, everybody to the right has the least number of oxygens. Because they have the least number of oxygens, they should end in ate or ite. Least is ite, yeah? So this would be chlorite. This guy would be chlorite. They clearly cannot have the same name for 2 different things. So when we have a group of 4, the one with the least number of oxygens in that group of 4 will end with ITE and actually start with hypo. So this is what is known as hypochlorite and chlorite. The guys to the left here have the most oxygens, which means they should end in ate. This would then be chlorate. This guy would also be chlorate, except for the same reasoning. We can't have the same name for 2 different things. So when you have a group of 4 that are related to each other, the one with the most oxygens will also start with per. So that is perchlorate, chlorate, chlorite, and hypochlorite. So what is the deal here? Well, it doesn't really matter the halogen that's in there. That is Cl, right? So it's chlorate. What do you think BrO3 minus would be? Not chlorate, but bromate, yeah? So this would be bromate, yeah? By the way, what do you think IO3 minus would be? Not chlorate, not bromate, but iodate, yeah? So again, you could actually swap out the halogen in that group of 4 for any of them, and they're all named basically the same, right? Now, how could I use this to my advantage? Well, if I remembered that this right here is chlorate, right? And I needed chlorite, I should take off one oxygen, right? That would move me here. If I needed hypochlorite, I should then move two oxygens off, right? It's two down the road there, and you would have it there. If I needed perchlorate, I should put on an oxygen. So again, you could kind of remember one name and formula and know how to adjust it based on whichever way you need to go. And that's a really good way to kind of group things together and remember, how to kind of adjust the names. Question on that there. Now, there are some other things that you'll see on this table, any of these tables. For example, right here, if you take this guy, CO3 2 minus, that is what is known as carbonate. If I take that guy and throw a hydrogen in front of it, an H plus, I get HCO3 minus. I put a hydrogen on it, +1, -2, -1. I basically put a hydrogen in front of it, so I call it hydrogen carbonate. Yeah, so because I put a hydrogen in front of it. Now, hydrogen carbonate is one where it's an old school type of name that's still used today. That is also known as bicarbonate. You get heartburn right about now, yeah? So you can take some bicarb there to help yourself out. Bicarbonate is used instead of hydrogen sometimes. For hydrogen carbonate, they'll sometimes use bicarbonate. You also see that with sulfate. It should be here somewhere, right here. This is sulfate that has a hydrogen on it, but is sometimes referred to as bisulfate. So that also, those two names you should be familiar with, bisulfate and bicarbonate. They are oftentimes used a lot still today. So people use those very commonly as well. But hydrogen carbonate or hydrogen sulfate is an appropriate name, and it's also used. Now, earlier we were talking about that you do not use prefixes, right, with like metals or anything like that, or Roman numerals. The one place where you could potentially see a prefix and a Roman numeral together is if the polyatomic ion actually has a prefix in its name. So here's an example right here. This name of this polyatomic ion is dichromate. And because that is the actual name of the polyatomic ion, you could potentially use it in, obviously, with a metal and have a Roman numeral and a prefix. That would be the only case where you would have a prefix and a Roman numeral, or like a prefix and a metal together. And it's really because the prefix is actually part of the polyatomic ion's name. So you can sort of adjust things, up and down. For example, if you look up here, we have maybe this here. Now let's just say, for example, I had one of those guys up there, which is PO4 3 minus, and I know that is phosphate. What would phosphite be? Does it have more or less oxygens? It should have less, right? So I should just take off one oxygen, right? Everything else stays the same, yeah? What would perphosphate be? Should I add or remove an oxygen from phosphate? Add, yeah? So it should be PO5 3 minus, right? What would hypophosphite be? I should remove an oxygen from phosphite, right? Yeah, and we'll end up with PO2 3 minus. So again, as you get used to memorizing these things, you just kind of know how to adjust them, and that's usually a pretty good way to do it. Again, you can remember all the eights or all the ites, and again, just kind of knowing how to move it and adjust it. It's a really good way to alleviate just flat out memorizing it. Or if you're good at just flat out memorizing, just flat out memorize the table, whichever way is best for you. Any questions on that there? All right, so let's try some here. We'll bother this table. It's not so written on here. So why don't we give some names here? Why don't you give the name for? Let's do. Let's do. Let's do. All right, so why don't you give the names for these three, and then why don't you give the formulas for ammonium sulfide? Why don't you do why don't you do calcium? Let's do calcium. Okay, so let's take a look. So I kind of throw it together so I got some room to write on this chart. Um, Clearly, like I said before, you do need to know these. So this is a pretty good chart to kind of know. Kind of has everything sort of organized by charges and stuff like that. All right, so we'll start with this one here. This is iron, which is a metal. This is a polyatomic ion, which is right here. And by the way, as you can see with this one, which is OH minus, there are some polyatomic ions that do end in IDE, and this is one of them. This is hydroxide. There's also cyanide. There's also azide. So there are a few that do end in IDE. So we would just want to kind of follow our normal sort of procedure. Here we do see a metal and a polyatomic ion. And as we talked about before, really the metal is always what you want to kind of focus on. And the metal here is iron, and the iron is a type 2 metal, which tells us we do need a Roman numeral. So again, as I mentioned before, most of the time you're going to find those polyatomic ions kind of hooked up with a metal. So because this guy is a type 2, we do need a Roman numeral. And that means the iron here, we're not sure of the charge. We again will know the charge of hydroxide, which is OH minus. And once again, there's not one of those, but two of them, which does give us a -2 left over there. And that means in this case, our iron has to be +2. So just like we did with type 2, we're going to go iron Roman numeral 2. Once again, for the positive charge there on our metal. And it doesn't matter how many polyatomic ions you have, you just use the name. So this would be iron 2 hydroxide. Any question on that name there? All right, looking at this one here, we again see a metal, which is magnesium. We see SO4, which is sulfate, and that is a polyatomic ion. It's right there. Here again, we're going to look at the metal, which is the most important thing. And that metal is group number 2 on the periodic table, which means it has a fixed positive charge and a type 1 metal. Once it's a type 1 metal, just like we did previously, we don't have to figure out anything else. We're just going to go magnesium, the whole name of the metal. And in this case, we're just going to go whole name of our polyatomic ion as well. So that would be magnesium sulfate in this case. Yeah. Any questions on that one there? Lastly, here we look at this guy, and we do see copper, which is a metal and a polyatomic ion. Once again, focusing our attention to our metal, which is going to really determine how we name it. Our metal of copper is a transition metal, so it is a type 2, which means we do need to figure out the charge. So once again here, we got our copper, we're not sure the charge. ClO is this guy right there, and that is hypochlorite. ClO minus, and there are two of them, which gives us an overall -2. And that means in this case, our copper is going to be +2. So again, we're going to go whole name of the metal. We do need the Roman numeral because copper is a type 2 metal. And once again here, we're going to roll with the whole name of our polyatomic ion, which in this case is hypochlorite in this case. Any questions on any of those names there? All right, so now that we have names, let's get some formulas. Going to follow really the same idea here. I see a metal with a Roman numeral, so I know cobalt should have a +2 charge. Cyanide is a polyatomic ion, so I'm looking for just the basic formula of cyanide, which is right here, by the way, and that is Cn-. Remember that these things, polyatomic ions, are basically ionic compounds, right? So we need to get to 0. So to get to 0 here, we would need not one of the Cn-, but we would need 2 to balance out the charge. And now we're ready to write our formula. We have 1 CO, and we have 2 of these guys, but because it is a polyatomic ion and more than 1, we do need the parentheses, right? And the number on the bottom there to indicate that there are 2 of those Cn- ions present. Question on that formula there. All right, next one, we'll go here, calcium, which is a metal, and that is group number 2, so +2. Phosphate is our guy down here, which is PO4 3-. Remember, this entire thing is a -3, and that is a +2. So our common number here again is 6, right, to get it to 0. So to get my calcium to 6, I need not 1, not 2, but 3 of them to get to +6. Get the phosphate to -6, I just need 2 of them. And again, that's going to balance it out. We have 1, 2, 3 of the calciums. We have 2 phosphates, so that's more than 1. So I need parentheses, a 4 and a 2 on the bottom there. And that would be our formula in this case, yeah. Any questions on that one there? Lastly, we have ammonium sulfide. Ammonium, remember, is not NH3. It is this polyatomic ion that has a charge. So that is NH4 plus. What is sulfide? Sulfide is? It is actually, most IDEs are elements, yeah? So it's actually just sulfur from the periodic table. And that is group number 6, which means it has a -2 charge, right? And when we put these together, we actually need more of the ammoniums, right? So we need a grand total of 2 of them. Because that is a polyatomic ion and I have 2 of them, I actually need parentheses, right? Na2. And I have just 1 of these guys, so I just need 1. And it should look something like that, yeah? Any questions on polyatomic ions there? So the key, unfortunately, is you got to memorize it, yeah? And again, you got to have those parentheses when you have more than 1. And like I said, I would say probably 99 times out of 100, you're going to probably have a metal with it. So again, just think about it like type 1 or type 2. And really the question is, do you need a Roman numeral or not for that metal? And that's what you kind of want to focus on. Again, the polyatomic ion part of it is not that important in terms of the naming part, because you're just going to use the whole name of it regardless of how many you have, right? But you do need to know the charges so you could properly balance out the formulas when you put them together to get to 0. Any questions on any of that there? All right, so obviously here, no, yes, all right. All right. Here's another table in case you hated the first 2. All right, so the last thing we're going to talk about in terms of naming are acids and how to name acids. And acids are substances that can produce hydrogen ions in solution. So for something to be an acid, it has the ability to release an H plus into a solution. And that's really what makes a solution acidic or basic, is how much of that free H plus is floating around. H plus in acid-base chemistry that we'll talk about at the very end of the semester is also sometimes referred to as a proton, because hydrogen has one proton, one electron, and no neutrons. And the way you become positively charged is to lose your electron. So that leaves it just a proton. So sometimes in acid-base chemistry, it's referred to as a proton for that reason. Now, when we go to name acids, by the way, what goes with this is typically bases. And a base is something that can produce hydroxide in solution. But we're going to focus in on how to name acids. And how we name acids all involves really this question that you want to ask yourself. It involves oxygen and whether or not your acid actually contains oxygen. If the answer is no oxygen, your acid will start like this. It will be called hydro something ic acid. Now, what makes something an acid is the ability to release that H plus. And when we talk about acids, the cation is always an H plus. So the positive ion in an acid 100% of the time is an H plus. So that is always the positive guy. The anion, which is our negative guy, is what is missing here. So whatever the negative guy is, it was what goes in that little spot there. Now, earlier, if you remember, we talked about HCl, say in the gas phase. And we called this guy in the gas phase hydrogen fluoride, right? If you take HCl, hydrogen chloride gas, and you throw it through some water, it will actually make a solution. And that will make an HCl solution that gets the aqueous symbol, the AQ symbol. And the AQ symbol means water environment. It means, I think we might have talked about it in an earlier chapter, it is a solution, a homogeneous mixture. And all acids will have the AQ symbol next to it. So when you see HCl with the AQ symbol, you know you are dealing with an acid rather than you're dealing with the gas version, basically, of HCl. And because it's an acid, we're going to name it like an acid. There's absolutely no oxygen in this acid. So this would be hydro. The negative ion here is Cl minus, right? Because the positive ion is H plus. Cl is chlorine or chloride, so this is hydrochloric acid. So that part comes from the negative ion that is present. HBr would be called what? Is there oxygen? There is no oxygen. So it's going to always start with hydro. The cation here is H plus. The anion is Br, which is group 7 on the periodic table, Br minus. So this is hydrobromic acid, yeah? So if you do not have oxygen, your acid will always start with hydro. It will always end in ic. The middle part that's missing is the name basically from the negative guy and acid at the end. Question on that there. Yeah. We haven't got there yet. So I started writing, I ran out of room. So I guess do the oxygen on the next page. Yeah. So, so right now it's no oxygen. So everything here is basically no oxygen. Yeah. And if it does have oxygen, it's still going to have H plus as its cation. And we do think of acids as ions because they are in solution, and it is that hydrogen that can be released. For example, when we talk about HCl here, it is this hydrogen that comes off in solution that becomes H plus that starts floating around. That's what is released by HCl that makes it an acid, and that H plus then goes off and floats around. So again, if you have no oxygen, this is how you do it, hydro. To answer your question, we will go this way with yes for oxygen, and we'll flip the page here so I have more room. So if the answer is, continuing on this way, yes, there is oxygen, your acid will contain one of those favorite things you just learned, a polyatomic ion. So if it does have oxygen, it most likely will contain a polyatomic ion. By the way, acids that do contain oxygen, they are sometimes referred to as oxyacids because they contain oxygen. So if you see the word oxyacids, it's a fancy way of saying, oh, that acid has oxygen in it, basically. So that is sometimes a term that's used. So what did we just learn about our polyatomic ions? They usually end in which two ways? They could end in ate or ite. And that is what you're going to be looking at in terms of your acid name. If it does contain oxygen and your polyatomic ion there ends in ate, your acid will be named something ick acid. Yeah. Again, a good way to remember this is you ate too much, you feel icky. Yes, so that's a good way to remember it as well. By the way, is there a hydro in this name? There is not. Yeah, so no hydro with this deal. So it's something ick acid. Yes, sir. No, this one ends in ick as well. What we're talking about 8 is the polyatomic ion that's present would be named, has an 8 in it. So let me give you an example so you can see it. If I take HNO3, right, and this is an acid, again, because it's an acid, the positive ion is H plus. The negative ion here is a polyatomic ion, and this is our friend that we just saw, NO3 minus. The name of NO3 minus is nitrate, ATE. So that's where we're talking about the ATE comes from. So because this acid actually contains nitrate, what we name it is nitric acid. So this is nitric acid because the polyatomic ion that is present is nitrate. Yeah. Now, if I had something like this, H2SO4, again, the positive ion here is H plus. SO4 is SO4 2 minus. That is what polyatomic ion? That is sulfate. Yeah. And because that's sulfate, this acid would be called sulfuric acid. Yeah. By the way, why is there 2 hydrogens? Yeah, so here's same idea. We want to balance out the charge. So really an acid is like an ionic compound. We want to balance it out to 0. So in this case, because this is -2, we do need that extra H plus to balance out the charge to 0. Yeah. Yeah. Are you talking about like back here on this to name it as an acid? Or? So to know it's an acid, it definitely should have an H in it. Okay. And it usually will have the little AQ symbol next to it, the aqueous symbol. And that's usually an acid. And they'll either ask you to name the acids, or like I said, they'll write a formula like this where you can see the hydrogen and the AQ, and that's a pretty good idea that it's probably an acid that you need to name. Same thing back here, like if you had this formula, again, you see the hydrogen, you see the AQ next to it, so it's probably a good idea that it's going to probably be an acid, even if it doesn't say that it is an acid. So that's really how you kind of know it. And then once you determine that it is an acid, you do then need to determine, kind of which way you name it. Does it have oxygen or not oxygen? All right, so if your polyatomic ion has oxygen, if your acid has oxygen, and the polyatomic ion ends in ite, which is our other option, right? You would then go something OUS acid. So for example, if I take HNO2, this again is an H plus. This is NO2 minus. NO2 minus is not nitrate, but it is nitrite, ITE, right? And because it ends in ITE, you're going to go with this OUS ending. And this is now going to be known as nitrous acid. Yeah. Question on that one there. What would H2SO3 be then? Was it? Say again? Hydrosulfuric acid? So first off, when we look at it, it is an acid. It does contain oxygen. And because it does contain oxygen, that takes hydro off the table. So hydro is only for no oxygen. So what we want to look at, right, is what is the polyatomic ion that's present. In this case, that is SO3 2 minus. So if SO4 2 minus is sulfate, SO3 2 minus should be sulfite, right? You could adjust down, right, one oxygen. And because that's sulfite, this will actually be sulfurous acid, yeah? OUS at the end there, yeah? And it'll be sulfurous acid. So if it has oxygen, you should not be using hydro, but you want to look at the polyatomic ion. And then if it ends in 8, that polyatomic ion, ic. If it ends in ite, OUS. If you have no oxygen, that is where you should use the hydro. Question on that there. So let's take a look at a few here just to finish it out here for our naming excursion. So why don't you take a second and name each of these acids and see what you come up with. And why don't you also write the formulas for these? Let's do. All right, so names on the left and formulas on the right. See what you come up with here. Okay, so since we're getting to the end here, got a few more minutes here. Let us kind of go through it together just to kind of, again, make sure you understand how we get to our answers here. So looking at this here, first off, I want to look at this. I see it's an acid, I see hydrogen, I see the aqueous symbol. The thing I want to first look at is oxygen or no oxygen, right? And in this case, there is no oxygen, right? So that tells me we are going to start with hydro, because there is no oxygen. Remember, this is H plus, and this would be S2 minus, which is why we have two H's there. And that's basically sulfur, right? So this is hydrosulfuric acid, right? And again, we got the hydro and the ic, and the middle part is kind of the sulfur part in this case, and we get to our acid. Question on that one there. Here we see hydrogen and aqueous. We do see oxygen, so that tells us polyatomic ion is what we need to look at. So this is H plus, and that would be ClO4 minus. ClO4 minus is perchlorate, right? That means that this would then be perchloric, right? 8-ic acid in this case, yeah? We actually do keep the front part of that name, right? Because it's part of the name of the polyatomic ion. So because that's perchlorate, we do need to keep the per part of it, yeah. You do not. So hydro is strictly for no oxygen, yeah. Yep. So that would then take us to this guy, which does not have oxygen. So this is where we're going to use hydro. So this is going to be hydro. Here we want to look at our negative guy, which is group 7, I minus, hydroiodic, right? Acid in this case, from iodine, right? And again, some of these names, they take out a few more letters than others and stuff like that. Here we do see oxygen, right, which tells us polyatomic ion we need to look at. So I have H plus, and that is CO3 2 minus. CO3 2 minus is carbonate, which means my acid should end in what? Ic or us? Ic. So this is going to be, if I could write, carbonic acid in this case. Any questions on any of those there? All right, so let's take a look at these on the right here to finish up with, so you see how you could go from name back to formula. So first off, when I see the top one here, hypochlorous acid, does this contain oxygen or no oxygen, this one? It does contain oxygen because there's hypo, but there's no hydro, right? So if it had hydro, I know it did not contain oxygen. So this makes me think polyatomic ion, right? And I know that if my acid ends in OUS, what did my polyatomic ion end in? So what you could essentially do is this: cross out the OUS and put ite. And that looks awful much like hypochlorite. And that will tell you the polyatomic ion that you need, which is hypochlorite, which is this guy. By the way, the acid positive guy is always H plus, right? So H plus is always the acid positive guy. So all you have to do now is put it together to equal 0. In this case, you just need one of each, right? A little aqueous to make it look all official, right? And you will have your acid in this case. How about the second one here? Does it contain oxygen or not? Second one does contain oxygen. Again, there's no hydro, right? So it tells me it contains oxygen. Polyatomic ion here, OUS, means it started with ite. So that is carbonite, which you may not be familiar with, but it does sound a lot like this guy, which is carbonate. And if that's carbonite, how many oxygens less should it have? Should have just one more oxygen less, right? Or one less oxygen is a better way of saying that. So that is CO2 2 minus, and the positive guy is H plus in this case, right? In this case, though, we will need two H pluses to balance out that charge, and that's going to give us H2CO2, and our aqueous symbol next to it to balance it out. Again, -2 + 1 + 2 balances out. Remember, again, for acids, H plus is always the positive guy. Yeah. Hydrofluoric, does it have oxygen? It does not, because it has hydro in it, right? So I know it doesn't have oxygen, so it's H plus. Fluoric is F minus, so putting those together will give me HF as hydrofluoric acid. Lastly here, phosphoric acid. There is no hydro there, which means it does contain oxygen and does have a polyatomic ion. And that polyatomic ion here, this ends in ic, the acid, which means if I cross that out, my polyatomic ion should end in 8. So now I can see phosphate basically, right? And phosphate is PO4 3 minus. How many hydrogens do I need to balance that out? I need not 1, not 2, but 3 of them, right, to balance out that -3 charge. That will give me a formula of H3PO4, and you will have your acid there. So again, acids, oxygen or no oxygen, hydro only for no oxygens, other guys polyatomic ions.